One more first order method for us to take a look at approximating the solutions to first order differential equations is a very powerful one, again, called the Runge-Kutta method. And the Runge-Kutta method actually has a number of steps or orders. We're going to take a look at one of the more popular ones called a fourth order. And essentially what we're going to be doing is we're going to be using a fourth degree Taylor polynomial to approximate the solution at a given point. And so what we're going to do is we have this system of equations that we have, and this is just the system necessary to be able to come up with the fourth degree polynomial. And so if we were to solve this algebraically, we would come up with a system of 11 equations and 13 unknowns. So in other words, it's going to be parametric because there's more unknowns than equations. And so by trial and error, somebody else went through and figured out that the most commonly used constants are going to be these. All right, so when we use our Runge-Kutta method, we're actually going to end up with a number of steps, and sometimes it's called a four-step Runge-Kutta because there's going to be 4 steps for us to be able to compute to get to the next y. Okay, so it looks intimidating, but it's really not all that bad. All right, so just like we did in the previous 2 examples, what we're going to do is we're going to explore how to do maybe one or two of the steps by hand, and then in the next video what I'm going to do is I'm going to use Excel to be able to figure these out. Alright, so we have the same differential that we've been working with, and we're going to approximate. Now we're probably not going to do 0.5, but at least we're going to do 0.1 and possibly 0.2 depending upon complexity, and we're going to figure out what the approximate solution is going to be based on what our solution to our differential is. Okay, so we already know the step size, we already know what the solution or the differential is, we actually know what the solution is too. Remember, the solution was y equals 2x minus 1 plus 3 over e to the 2x. All right, we solved that a while ago. All right, so let's see how close the Runge-Kutta method can get us. So let's start by finding what k1 is. All right, so this is just for the iteration 1. All right, so this is to approximate y at 0.1. All right, so k1 is going to be equal to 0.1. And again, we're just doing this by hand, so this is going to be 0.1 times the function, which is going to be 4 at x. Now the current x is going to be 0, and the current y is 2. So this is going to be 4 times 0 minus 2 times 2. Right? And this isn't too difficult to compute. That just gives us a negative 0.4. So let's hold on to that, because what you'll notice is we need that to be able to compute k2. k2 by hand is going to be 0.1 times 4 times the current x plus a half of the step. So that's going to be current x plus 1/2 times 0.1 minus 2 times the current y, which is 2, plus a half of negative 0.4. And when we go through and compute that, that's just going to be negative 0.34. And again, we're going to hold on to that number because we need that to be able to compute k3. Now the good news about k3 is it's the exact same formula as k2, except we're just going to replace 0.4 with 0.34. So for k3, that's going to be equal to 0.1 times the quantity of 4 times 0 plus a half times 0.1 minus 2 plus a half of negative 0.34 this time. All right? And when we compute that out, that's going to be equal to a negative 0.346 this time. And then finally for k4, k4 is now going to be equal to the step size times the function at xn plus h, yn at k plus 3. All right, so that's going to be 0.1 times 4 times the current x plus the step size, which is 0.1, minus 2 times the current y plus k3, which was negative 0.346. Okay. And then if we stick that into our calculator, we're going to end up with a negative 0.2908. All right, now we're gauged to be able to figure out what the next y value is. All right, in our formula for yn plus 1, we're going to take the previous y, and we're going to add to that a sixth of k1 plus 2 of k2s, 2 of k3s plus k4. So that's going to be equal to 2 plus 1/6. Remember, for k1, we got negative 0.4, plus 2 of k2, which was negative 0.34, plus 2 of k3, which was negative 0.346, and then finally plus a negative 0.2908. And we're going to stick that into our calculators, and that's going to give us 1.6562. All right, now you should go through and make sure that you can find these in your calculators for yourselves. The question is at this point, how good of an approximation is this? Well, let's go ahead and find y at 0.1, and y at 0.1 is 2 times 0.1. And by the way, we're using the actual solution. So we're going back and we're using the actual solution to figure out what y at 0.1 is. Minus 1 plus 3 over e to the 2 times 1. Right? Now we could write this as negative 0.8 plus 3 over e squared. All right, but let's just throw that into our calculator and see what we get. All right, so just give me a moment. I did not prepare this part. So we have 0.2 minus 1 plus 3 divided by our e to the 2. All right, and unfortunately, maybe I made a calculator somewhere in here. Oh, this should be a 0.1. That's why. Let's try that again. So we end up with, by computation, 1.6566192259. All right, now how accurate is that? Well, check this out. We're actually accurate out to the thousandths place, and if you were to round it, it would actually be accurate to the 10,000ths place. All right, so this is just one iteration of being able to utilize the Runge-Kutta method. Now, obviously, if we were to use the next iteration, then we'd have to replace all the values for yn and xn, etc. All right, so just to give you an idea, and I'm not going to do all of these, but let's say I wanted to find y at 0.2. I would have to start the process over again. Now xn is going to be equal to 0.1, and then yn is going to be equal to the 1.6562 that we just found in the previous y. All right, so you can see that this is going to be taxing as we go through and do this again. All right, so what we'll do is we'll take a look in the next video as to how to utilize Excel to be able to get to y at 0.5. We're going to look at the error, and we're going to see how good of an approximation we can get.